Okay, in this video, what we're going to do is we're going to define the derivative. And we're going to do that two different ways, and then we're going to set up a group of basic rules that can be used to calculate some simple derivatives. In order to do this, we need to do a little bit of investigation into what Newton was trying to do. I think it helps to set that stage. Newton was ultimately trying to investigate gravity, or the force of attraction between any two objects that have mass. And so the basic model of gravity is that you have a falling object and that you can chart pretty quickly its position at, let's say, time 1 and its position at time 2. That's pretty easy to do. So we can get an idea of where its position is over time. What Newton wanted to do is he wanted to look at the acceleration of these objects, because he had some thoughts about that. And to do acceleration, you can't just observe acceleration. You can observe position, but you can't observe acceleration. So what Newton notices is that, well, acceleration has to do with the change of velocity at 2 times. So we'll say velocity at time 2 minus velocity at time 1 over time 2 minus time 1. This gives me an average velocity, or an average acceleration, right? Over that span from 2 to 1. But velocity can't be observed either, so you need to derive that from position. So you take the position at time 2, you subtract the position at time 1, and then you look at the difference between the two times. So these are basically like the slope formula, right? It's y2 minus y1 over x2 minus x1, and this is where you're going to get this like Newtonian difference, okay? But what Newton gets here is that he doesn't want to know what is the velocity on average over this. He wants to know what's the velocity at time 1 instantly, right? So what he does is he applies a limit here. The limit as t2 approaches t1 gives me the instantaneous velocity at time 1. Likewise, the limit as t2 approaches t1 of the velocity will give me the instantaneous acceleration at t1. And the earth-shattering thing that Newton noticed, now granted he was before the metric system, so he would have noticed that this happened at a rate at 16 feet per second per second. Now, we're post-metric, so we say that this is 9.8 meters per second, right? So position is the meters. This is a depth of meters. This is meters per second because it's divided by time, and then per second again because it's divided by time again. So that's why we get this meters per second squared. Okay, so just to give you an idea of how fast that is, your Olympic divers stand on a 10-meter platform. In actuality, if they jump off that platform and plummet to the water below, that will take them approximately 1 second from the time they leave the platform to the time that they splash in the water. Okay, so enough about Newton. Let's see how this plays out for our calculus class. Okay, so what we've basically just established is what's called the intuitive, or I'm going to call the intuitive definition of the derivative. So velocity and acceleration and position are all continuous functions. So if f is a continuous function, it's important that f has to be continuous, then the derivative of f at point A with respect to x is going to be the limit as x approaches a of f of x, so this is like the position at time 2, minus f of a, this is like the position at time 1, over time 2 minus time 1. So this is very much an intuitive definition. And this is actually a valid definition of the derivative. It's not the one that we most commonly use, but it's the one that makes like the most intuitive sense. So what we do is, to get to the other more classical definition of the derivative, we make a change in variable. And we let h be equal to x minus a. So we're going to let h be equal to the denominator of h being equal to x minus a. A little bit of algebra, and that means that x is going to be equal to h plus a. So if I just move the a to the other side and flip things around a little bit, I can get that. So we also have to note that as x approaches a, so as these two things approach each other, x approaches a, that means that h, which is their difference, is going to approach 0. Okay, so this means we can do, if I rewrite this in terms of h, I'm going to get the classical definition of the derivative. Okay, so let's take, this means that the derivative of f a with respect to x is equal to the limit as x, let's see, now wait a minute, we're not x anymore. We are, let's see, x approaches a is now going to be replaced with h approaches 0. Okay, and we just said above that if h is x minus a, then x is h plus a. Okay, I can also write that as a plus h, I think is how we more commonly write it. A plus h minus f of a still, all over x minus a is what we defined as h. So this is all over h. So this here is the definition of the derivative that you most often see, is that some variable h is going to 0. If I'm a little bit off from a, and that goes to 0, then the change in the f over h, which is the change in the x, should give me the instantaneous rate of change. Okay, so we'll look at this a little bit further in a few minutes, but I want to get into some of the basic derivative rules. Okay, so in this chapter, you're going to get a bunch of rules for the derivative. Today, we're going to pick up 7 basic derivative rules. And what kind of derivative, there we go, derivative, there we go, it's an A, derivative rules. All right, so let's take a look. The first one is that if I take the derivative of some constant, I get 0, because the constant isn't changing, so its instantaneous rate of change, it makes sense to be 0. If I take the derivative of the function y equals x, so that thing, well, its slope doesn't change, it's just its slope, which is 1. So that's pretty straightforward. Let's look at number 3 here. This is like what we're going to call the power rule. So I'm going to take the derivative of x to the nth, right? So x is a variable, n is a constant. If I take that derivative, well, I bring the n out front, and then I drop the power by 1. Well, let's look at this as it plays out with our definition of the derivative and see how that plays out. Okay, so let's look at something pretty simple. Let's let f of x be equal to x squared. So according to our derivative rule, the derivative of f at some point x with respect to x should be equal to, well, we bring the 2 down in front, it should give me 2x to the first. So let's see how this plays out with our limit rule. So this, the derivative of f at x over dx, should equal to the limit as h approaches 0 of f of x plus h minus f of x over h, right? So that's kind of my classical definition. So let's see, this is the limit as h approaches 0 of x plus h squared, because that would be f of x plus h, minus x squared over h. Okay, so what do we get here? We get the limit as h approaches 0 of, let's see, that's going to be x squared plus 2xh plus h squared minus x squared over h. So something neat happens here. This x squared and this x squared cancel. So this now becomes the limit as h approaches 0 of 2xh plus h squared over h. These both have h's in them. So this is going to give me the limit as h approaches 0 of 2x plus h. When I divide the h, right, h divided by h, those cancel, and h squared divided by h just gives me h. Well, if I let h go to 0, this is just going to be 2x. Haha! Which is what I expected, right? 2x to the first, 2x. So this power rule is just like a really fast way of doing all of this limit stuff. So we really want to get these rules down because we don't want to have to get back to the definition. Ever. Okay, so let's look. Okay, so at this point we have three rules, right? The derivative with respect to x of a constant is 0. Rule number 2, the derivative with respect to x of x is 1. And number 3, which is what we're calling the power rule, is x to the n is going to be n times x to the n minus 1. And you could explore this further with other, power functions, but right now we're kind of there. Okay, so the fourth rule is that if you have the derivative of a constant times the function, well, that the constant just comes along. So it's the same as the constant times the derivative of the function. So you just bring the constant along and the function stays where it is. So this could be useful because sometimes you can factor out a constant and then you don't have to deal with everything. Number 5 is what we're going to call the addition rule. Is that if I take f of x and it's either adding or subtracting a g of x, then this is just simply the derivative of f of x, and it'll be plus or minus the derivative of g of x. So if you have a sum or a difference, you can just handle the two derivatives separately. So that's pretty straightforward. Number 6 is not, it's what we call the product rule. Okay, so the product rule says that if I have the derivative of f of x times g of x, then this is going to be f of x times the derivative of g of x plus g of x times the derivative of f of x. So sometimes this is read as first times the derivative of the second plus second times the derivative of the first. So that's a little bit fancier. If you want to go back and look at the limit theory and see how that works, you're more than welcome to. If you don't trust it, I would say prove it yourself, but that one works. Okay, so the last one, the big number 7, is going to be what we call the quotient rule, and this is the derivative of two things that are being divided, right? F of x over g of x, provided that g of x does not equal 0, is g of x times, and I'm going to use this notation, f prime of x, that just means the derivative of f at x, minus f of x times g prime of x. So that's the derivative of g at x over g squared of x. So we're going to actually square the g of x. So another way of reading this is it's low d high minus high d low over low squared. So low d high minus high, I guess that should be high, H-I-G-H, high d low over low squared. Okay, low d high over high minus high d low over low squared is the quotient rule. Okay, so this is something that you do want to commit to memory. Okay, all of these can be proven by direct appeal to the definitions set above. Okay, so two definitions of a derivative. df at a over dx can either equal the limit as x approaches a of f of a minus f of x. Sorry, got that backwards. Don't want to mess that up. F of x minus f of a over x minus a, which can be rewritten as the limit as h approaches 0 of f of a plus h minus f of a over h. And then we got a bunch of rules, right? The derivative with respect to x of a constant is 0. 2, the derivative with respect to x of x is 1. 3, the derivative with respect to x of x to the n is going to be n times x to the n minus 1. Number 4, the derivative with respect to x of a constant times f of x is going to equal the constant times the derivative with respect to x of f of x. 5, we get the sum rule. The derivative of f plus g with respect to x is the derivative with respect to x plus or minus the derivative with respect to x of g. We get a number 6, a product rule of f times g is going to be the first times the derivative of the second plus the second times the derivative of the first. And finally, the derivative with respect to x of f over g is going to be low d high minus high d low over low squared. Alright, so there's your basic derivative rules kind of on a postcard and the two definitions of a derivative. These are things you need to know, be procedurally fluent with, and commit to memory.